In previous videos, I've talked about how to assess arguments from the logical point of view, and that when assessing arguments using logic, what we're mainly interested in is the connection between the premises and the conclusion. How well do the premises support the conclusion? And since we're interested mainly in that connection, the first thing we do in evaluating an argument is look for the strongest connection, the tightest connection between the premises and the conclusion, and we call that a valid argument. It's the sort of connection that guarantees that the conclusion is true whenever the premises are true. And there are different ways of defining validity, and they are, for the most part, equivalent. We can say an argument is valid when necessarily if the premises are true, the conclusion must be true, or when the premises guarantee the truth of the conclusion, or when the conclusion follows necessarily from the premises, or when it is impossible for the premises to be true and for the conclusion to be false, or when the truth of the premises necessitate the truth of the conclusion. Our most formal definition, the one that is perhaps the most precise, is the one that says an argument is valid when it is impossible for the premises to be true and for the conclusion to be false. We can also define validity using the sort of definition that captures what we do when we assess an argument for validity, or the main way of assessing an argument for validity, which is to assume the premises are true and ask ourselves, assuming the premises are true, would the conclusion have to be true? So we could say an argument is valid when, assuming the premises are true, the conclusion would have to be true. And what that is saying is that there is this 100% guarantee between the premises and the conclusion, such that whenever the premises of a valid argument are true, the conclusion has got to be true. There's no slippage. There can never be a breakdown between the premises and the conclusion. If there could be, then we look to see whether the argument is strong or weak. But when we're looking for that strongest connection, we're looking for that 100% guarantee, that bridge between the premises and the conclusion that could never break down. So returning then to our most formal definition of validity, we're going to focus on that now, because to test arguments using truth tables, we need to focus on that formal definition, because that formal definition brings out what we're trying to do when we test arguments for validity using truth tables. So an argument is valid when it is impossible for the premises to be true and for the conclusion to be false. In other words, a valid argument can never have this actually true premises and an actually false conclusion. That's not to say that when an argument is valid, we're saying anything about the actual truth values of the premises and the conclusion. We're not saying that the premises are actually true. We're not saying that the conclusion is actually true. All we're saying is this: a valid argument could never have this one thing, true premises and a false conclusion. Valid arguments can come in all shapes and sizes. They can have true premises and a true conclusion, false premises and a false conclusion, but the one thing they can never, ever, ever have is true premises and a false conclusion. This is what the table here is showing. You can see that valid and invalid arguments can have true premises and a true conclusion. They can both have that. Valid and invalid arguments can have false premises and a false conclusion. Or they can have false premises and a true conclusion. But the one thing they can't both have is true premises and a false conclusion. Only an invalid argument could have that. Knowing that, we can assess an argument for validity on occasion by knowing the possible or actual truth values of the premises and the conclusion. So suppose I'm going to give you an argument, and instead of giving you the actual argument, all I tell you is that the premises of this argument are actually true, and the conclusion is actually true. Do you have enough information at that point to know whether the argument is valid or invalid? No, because both valid and invalid arguments can have true premises and a true conclusion. So that information doesn't tell you enough in this case to assess the argument for validity. Or suppose I'm going to give you an argument, and I don't actually give you the argument. All I tell you is this: the premises are actually false, and the conclusion is actually true. Is that enough information to know if the argument is valid? And again, the answer is no, because valid and invalid arguments can have false premises and a true conclusion. So how are we supposed to know which one it is? If valid and invalid arguments can have that, for all we know it's valid, for all we know it's invalid. Not enough information. Or suppose I tell you I'm going to give you an argument, but instead of giving you the argument, all I tell you is this: the argument's premises are false, and the conclusion is false. Is that enough information to know if the argument is valid? And once again, the answer is no. Why? Because valid and invalid arguments can have false premises and a false conclusion. Finally, I say I'm going to give you an argument, but I don't actually give you the argument. All I tell you is this: the premises of this argument are actually true, and the conclusion is actually false. In that case, is that enough information to know if the argument is valid or invalid? Yes, the argument is invalid. We know that right off the bat, because a valid argument could never actually have true premises and a false conclusion. So that's the only case in which knowing the actual truth values of the premises and the conclusion tells us anything. And we're going to use that and exploit that bit of knowledge to test arguments for validity using truth tables. Don't fall into the trap of thinking that just because an argument has all true premises and a true conclusion, all is well. Invalid arguments can have true premises and a true conclusion. Like some fruits are green, some fruits are apples, therefore some fruits are green apples. Turns out that argument is invalid, even though the premises are true and the conclusion is true. You can also have valid arguments that have true premises and a true conclusion, like all dogs are mammals, some dogs are brown, therefore some mammals are brown. So if we just know of an argument that the premises are true and the conclusion is true, that's not enough. We have to actually look at the argument, because it could go one way or the other. Or don't think that because an argument is all false, because the premises and the conclusion are false, that the argument must be a bad one, because valid arguments could have false premises and a false conclusion, like either Joe Biden is the president or George Bush is the president. Premise 2, Joe Biden is not the president. Conclusion, therefore, George Bush is the president. This contains nothing but false claims. But nevertheless, from a logical point of view, it's a great argument. In fact, we call this style of argument disjunctive syllogism, and it's a valid form. But invalid arguments can have false premises and a false conclusion, like all wines are whiskeys, ginger ale is a whiskey, therefore ginger ale is a wine. That's an invalid argument. All of it's false, but a valid argument can have all false premises and a false conclusion. So knowing just that an argument, whatever that argument may be, has actually false premises and an actually false conclusion doesn't tell us anything. The only time knowing the actual truth values tells us anything is when the premises are actually true and the conclusion is actually false, because that's the one and only one case the argument can't be valid. A valid argument could have everything. It could have true premises and a true conclusion, false premises and a false conclusion, false premises and a true conclusion. But a valid argument could never have true premises and a false conclusion. So when we're talking about the validity of an argument, remember that validity is primarily a matter of form, which is something we exploit when we memorize some of the famous valid forms. Because, like for modus ponens, if you get the right form, the argument is guaranteed to be valid. And a good logical form, like modus ponens, is one that will never allow for true premises and a false conclusion. It might allow for all sorts of other things, but never true premises and a false conclusion. Now we're saying that when an argument is valid, we're not saying that the the premises are actually true and the conclusion is actually true. Or when we say an argument is invalid, we're not saying that the premises are actually true and the conclusion is actually false. Validity is a possibility claim. It's saying, when an argument is valid, that this is impossible, that this could never, ever happen, that the premises end up being true and the conclusion false. So we're going to test arguments for validity by seeing if the argument form ever allows for true premises and a false conclusion. And we'll do that by using truth tables, because the truth tables will capture every possible way in which the premises and the conclusion of the argument can be true or false. And we'll see if, given all those possible ways, there's ever an instance in which we get true premises and a false conclusion. So initially, this is what it's going to look like. We're going to fill out a truth table and then look across the premises and the conclusion and see if there's ever a case in which we get true premises and a false conclusion. And if there is such a case, if that shows us that it is possible, which shows us that the argument is invalid. If there is never such a case, that shows us that it's impossible for the premises to be true and for the conclusion to be false. And that's just the definition of validity. Let's start off with the valid argument form and use the truth table method to show that this argument is valid. What you see here is an instance of modus ponens. This argument says if A is true, then B follows. The second premise says A is true, so the conclusion tells us B followed. To assess this argument using truth tables, we need to represent the premises and the conclusion on just one line instead of vertically, as we see here. So we're going to take a truth table and write out the premises and the conclusion on the top line. And we'll know which parts of the premises because we'll separate the premises with a comma, and we'll know which part is the conclusion because the conclusion will occur after what we call the triple dot. So here's our first premise. If A is true, then B follows. Here's our second premise, A is true. And here's our conclusion, B followed. Now that we have the argument set up on a single line, we need to set up the left side of the truth table. And to do that, the first thing we're going to do is pull out the statement letters to the left side of the truth table. So here we have an A, so let's pull that out to the left side, and a B. And are there any others? No, we just have A and B as the only statement letters that occur in this argument. Now we have to figure out how to fill out all the truth values in this area here. We could try it in a random way and say, well, I suppose A could be true and B could be true, and perhaps, well, A could be false and B could be false, and go about it in this way where we're kind of just guessing and going with what's off the top of our head. Whereas we need really a formula to make sure that when we're filling out the left side of this truth table, we capture all the possible truth values over here. We need to capture all the possible combinations in which A and B can be true and false. So we've pulled out the statement letters to the left. Now we need to determine the number of rows on the left-hand side so we can figure out how to set up the truth values. And the formula is 2 to the n, where n represents the number of letters. So here we have 2 letters. 2 to the n would be 2 to the second. 2 to the second is 2 times 2, which equals 4. So we're going to have 4 rows for this argument. Here's 1, 2, 3, 4. The next step, once we figured out how many rows the truth table is going to have, is to start at the left-hand side, the very far left, with the first column, which will be the column under the A, and in a sense, divide and conquer. We've got 4 rows, so we're going to divide in half and do top half T's and the bottom half F's. So top half T's, bottom half F's. We did groups of 2 there. So take what we did and divide in half again. So since we did groups of 2, 2 divided by 2 equals 1, we're just going to go by ones. We're going to do T, 1T, 1F, 1T, 1F. So again, we pulled out the statement letters to the left. We figured out how many rows we were going to have with that formula, 2 to the n, which was 2 to the second, which gave us 4. Then we started on the left-hand side, knowing that we had 4 rows. We divided in half and did top half T's, bottom half F's, and then the last column is always just alternating, T, F, T, F. This explains why we set up the truth tables the way we do when we give the truth conditions for an AND claim or an OR claim or an if-then claim or an if and only if claim. The left side for each of them is set up in the exact same way. Here we have 2 variables, and those are pulled out to the left. And then since we have 2 variables, we do 2 to the n, or 2 to the second, which gives us 4. So we have 4 rows, 1, 2, 3, 4. We start on the left-hand side, divide and conquer. Do top half T's, bottom half F's. And then the last column is always just alternating, T, F, T, F. That's the same for all of these, except for the negation, for the tilde. That's different because we only have 1 variable there. But the rest of these are all done in exactly the same way. Let's see what happens when we have 3 letters. So here's an argument, if A then B, and if A then C, then the conclusion is B then C. First step is always to pull out the statement letters to the left. So we have an A, we've got a B, and we've got a C. And there aren't any letters besides those 3. Now we need to figure out how many rows we're going to have for this truth table. So we use the formula, 2 to the n, 2 to the number of letters we have. So 2 to the third. That's 2 times 2, which equals 4, times 2, which equals 8. So that means we are going to have 8 rows altogether. 1, 2, 3, 4, 5, 6, 7, and 8. Now go to the very left-hand side. Start with the leftmost letter. Divide and conquer. Do the top half of the row T and the bottom half of the rows F. So since we have 8 rows, we'll do top half T's, which is 4 T's. Bottom half will be F's, so 4 F's. Now divide in half again. Since we did groups of 4, let's divide that in half and we get 2. So now let's do groups of 2. So under the B we get 2 T's, then 2 F's, 2 T's, and 2 F's. And the last column is always just alternating, T, F, T, F, T, F, T, F. And here, we've managed to capture every possible arrangement of truth values for A, B, and C, because A, B, and C could all possibly be true at the same time, or they could all possibly be false at the same time, or A could be false and B could be false, but C true. But instead of listing that randomly and trying to make sure we capture all the relevant possibilities, we've got this formula that guarantees that we will get all the right possibilities out here. What happens then when we have just one letter? So consider this argument. It's got one premise, A. And then the conclusion, A if and only if A. You're unlikely to see an argument like this, but nevertheless this is an argument. And so the process is the same. Pull out the statement letters to the left. Well, there's only one of them, so A. Plug in the number of statement letters into the formula 2 to the n. So 2 to the first, which is 2. That means we're going to have 2 rows. Do top half T's, bottom half F's, but that's easy since we have only 2 rows, just one T and one F. And that's how we do the truth table for a tilde. You have one T and one F. It's using the same formula, that we used for the other truth tables. Now, if you don't want to think in terms of 2 to the n, because that might be a little off-putting for you, there's another way of remembering how many rows you need to write down. If you have one letter, you're going to get 2 rows. If you have 2 letters, 2 statement letters, you'll write out 4 rows. If you have 3 statement letters, you'll write out 8 rows. If you have 4 statement letters, you'll write out 16 rows. And God forbid we have anything this long. If we have 5 statement letters, we would have 32 rows. So you can just remember this, or remember the formula 2 to the n, and use that to calculate the number of rows. Let's return then to our original argument, the modus ponens argument. We've got the premises and the conclusion listed on one line at the top of the truth table. We pulled out the statement letters to the left. And over here, we've captured every possible arrangement of truth values. So what's the next step? Well, now what we do is something you're already familiar with. We've really gotten past the point of introducing the stuff that's novel. What we'll now look at is something you're already pretty much capable of doing, but we're going to do it in a different kind of setting. First of all, let's look at line 1. It says A is true and B is true. Let's look at the first premise. So we think A is true and B is true. And for a conditional, if the antecedent is true and the consequent is true, the whole conditional is true. That looks maybe confusing because there's a lot going on up here. You have all this stuff over here to the right. You got all this stuff going on down here, and it just doesn't look familiar. But suppose I were to do this. Suppose I were to give you a claim. If A is true, then B follows. And I were to tell you, suppose A is true and B is true. Could you figure out the truth value for that claim? Well, what does a conditional say? Conditional says that whenever the left side of a conditional is true, whenever the antecedent is true and the consequent is true, the whole thing is true. So this would be true. But that's precisely what we did over here. We had A is true, B is true, and so we imagine there was a true under here, and a true under the B, a true under the A, and the true under the B, and according to the truth table for a conditional, when the antecedent and consequent are true, the conditional is true. So we wrote the true underneath that arrow. Even though we're doing one big problem here, this first step was pretty much a matter of doing one simple problem, but doing it in a larger setting with all this other stuff that could possibly distract us. But it's really just this problem. If A is true, then B follows. And we're told A is true and B is true. So that means that the arrow, the conditional, would be true. If you can do that, then you can do the truth table for this argument. Now the next step, we go down to the next line, and we see that we have A is true and B is false. So we're going to assume A is true and B is false. What happens when a conditional has a true antecedent and a false consequent? Well, that's the only time a conditional is false. But instead of thinking of it in terms of that broader context, let's just isolate the conditional and just imagine that you're told A is true and B is false. You have a conditional, the antecedent is true and the consequent is false. Well, what do you know? Well, for the truth table for a conditional, there's only one case in which it's false. True antecedent, false consequent. And here we have true antecedent, false consequent. So that is the one case in which a conditional is false. But that's what we've written over here. Since we were told that A is true and B is false, we wrote false underneath the arrow. Let's look at the next line. We've done the first two. Just keep going or moving our way downward. The third line. In this case, we're told A is false and B is true. When you have a conditional and it's only false in one case, when you have a true antecedent and a false consequent, every other time then it's going to be true. So in this case, it's going to be true. We can think of that more easily by detaching the premise from the argument and just thinking about the premise by itself. Suppose you're given the claim, if A is true, then B follows, and you're told A is false and B is true. Well, according to the truth table for a conditional, whenever the antecedent is false and the consequent is true, the conditional is true. So we would write true underneath the arrow there. But that's basically what we did in this broader context. We were told A is false, B is true. So the antecedent is false, consequent is true. And according to the truth table for a conditional, that makes the whole claim true. And the same for this last part here, the fourth line. Here we're told A is false and B is false. Since a conditional is false in only one case, when you have a true antecedent and a false consequent, and since this isn't one of those cases, this conditional is going to be true. So what we've done here in this first part of the truth table for an argument is we've done, in a sense, 4 separate problems. We treated A then B like 4 separate problems. First, we imagined, according to the first line, that A was true and B was true. And then we imagined, according to the second line, that A was true and B was false. And then we imagined, according to the third line, that A was false and B was true, and so on. So even though we're doing this all in one area, and it looks pretty complicated, it's not. Because while we're doing this, we're really just focusing on little bits at a time. First thing we focus on is just this right here. A is true and B is true, and we get the true underneath the arrow. This stuff isn't even in play yet. It's not in play until we finish all the rows underneath that arrow. Now that we have finished the first premise, let's go on to the second premise, the A claim. This is going to be pretty easy because we don't have to figure anything out. We just write down what they tell us. So the first row, A is true, so we just write down true here. Second row, A is true, so write down true. Third row, A is false. Fourth row, A is false. We've got that one done now. So the only thing left to do is the conclusion. Again, start at the first row. This is going to be easy. We don't have to figure anything out. We just have to write down what they tell us. So first row, we're told B is true. Second row, we're told B is false. Third row, that B is true. And fourth row, B is false. So what we've done here is taken 12 different problems and pack them into one. Here was a problem, here was one, here was one, here was one, here was one, and so on. And you can do those problems on their own. If you can do them on their own, then you can do this. The only new thing is the context and trying to keep everything straight and just going line by line, taking your time and being sure to focus on the relevant portion of the truth table. So now that we've done this, we're ready to assess the argument for validity. And I said earlier that a valid argument could have every arrangement of truth values. It could have false premises and a false conclusion, true premises and a true conclusion, except it could never have true premises and a false conclusion. So that's what we want to look for. Since on this left side we've captured every possibility, we want to see if any of these lines give us true premises and a false conclusion. So let's just go line by line. So first line, we get true, true, and true. So didn't get it there. Next line, we get a false premise, true premise, false conclusion. Didn't get it there. Third line, we get a true premise, a false premise, and a true conclusion. So didn't get it there. And finally, the last line, we get a true premise, a false premise, and a false conclusion. We didn't get it there. We weren't able to get true premises and a false conclusion, which means, since on this side, we've captured every possibility, every way in which A and B can be true or false, there is just no way the premises of this argument could ever be true and the conclusion false. In other words, it's impossible for the premises to be true and for the conclusion to be false. And therefore, this argument is valid. Now, we already knew it was valid because this is modus ponens, one of the most famous valid argument forms. But what we've done here is proven why it's valid. In other words, assuming the premises are true, the conclusion would have to be true. There's no way that the premises of this argument could be true and the conclusion false. Let's then look at another style of argument, a famous invalid form. This is a famous invalid form because it looks a lot like a valid form. It looks a lot like modus ponens, and so we tend to mistake it for modus ponens when it's invalid, and we call this form affirming the consequent. Let's prove that this argument form is invalid with a truth table. So we begin by writing out this argument horizontally instead of vertically. We write out the premises and the conclusion all in one line. And we're sure to separate the premises with a comma, and then the conclusion is separated from everything else with the triple dot. First step is always to pull out the statement letters to the left. So we have an A, we have a B, just like last time. Now that we have the statement letters out to the left, we have to figure out how many rows for this truth table we're going to have. And we figure that out by plugging in the formula 2 to the n. So 2 times 2 to the number of statement letters we have. We have 2 letters, so 2 to the second equals 4. So we're going to have 4 rows. 1, 2, 3, 4. What's next? Well, now that we've got our rows set up, we divide and conquer. Start on the left-hand side. Do top half T's, bottom half F's. Since we only have 4 rows, when we start on the left-hand side, we'll do top half T's, that's 2 T's, and then 2 F's. And the last column is always just alternating. T, F, T, F. Now the process here is the same as last time. We've got the truth table set up. Now we just go line by line and premise by premise or conclusion and just take them one at a time and put in the resulting truth value. So this first line here, it says, imagine A is true and B is true. Okay? Well, in a conditional, if the antecedent is true and the consequent is true, the whole conditional is true. But we can think of this as its own separate problem. Suppose you're just given this claim: if A is true, then B follows. And suppose that you know the truth tables well enough that you know that if A is true and B is true, this conditional has got to be true. Because that's what the truth table says. It says when the antecedent is true and the consequent is true, the conditional is true. So this looks pretty simple. But what we've done is we've taken this simple thing and transported it into this much more complicated claim. But the complicated claim is really just made up of these simple parts. So we've got the first line done. Now let's go down to the next line. It tells us to assume that A is true and B is false. Well, a conditional is false in only one case, when the antecedent is true and the consequent is false. So we get a false there. Again, we can just think of this as a separate problem. Suppose you're given a conditional and you're told the antecedent is true and the consequent is false. Well, what would that be? Well, according to the truth table for a conditional, there's only one case in which a conditional is false. When you have a true antecedent and a false consequent, then you get false, which is what we have here. True antecedent, false consequent. So this is going to be false. But instead of just writing this out in its own separate area as a simple problem, we can think of it in this larger context, a part of this more complicated problem, but merely as a simple component of this larger, more complicated problem. We're told, again, A is true, B is false, and we know that would make that conditional false. So we finished lines 1 and lines 2. Now let's go down to the next line. This line tells us to imagine that A is false and B is true this time. So A is false, B is true. There's only one case in which a conditional is false. It's this one. True antecedent, false consequent. Every other time it's true. So since this case isn't a case in which the antecedent is true and the consequent is false, this has got to be true. But let's think of it as a separate problem. You're given a conditional claim, and you're told this, that A is false, B is true. Well, knowing the truth conditions for a conditional, when the antecedent is false and the consequent is true, the whole thing is true. In fact, anytime the antecedent of a conditional is false, the conditional is true. That's something to keep in mind. That's a nice shortcut because you'll get lots of conditionals with a false antecedent. And once you get one with a false antecedent, you won't even have to worry about what's in the consequent. You automatically know the conditional's got to be true. Why? Well, these are the only two cases in which the antecedent is false, and in both cases, the conditional is true. So we write true underneath the arrow here. Well, that's what we did originally in our larger truth table. We were told A is false, B is true, so we wrote down true. And our last row tells us that A is false and B is false. And like I just said, whenever a conditional has a false antecedent, the conditional is true. So we finished our first column, we finished our first premise. Now let's go to the second premise. In a sense, we're kind of starting over. Forget about what we've done previously. Just focus on this single premise here. It's kind of hard because it's easy for this stuff over here and for that stuff to get in the way. So you have to kind of tune them out and focus on the B. And this says, for the first line, B is true. So we write true underneath the B there. And the second line, it says B is false. So we write false under the B. Third line says B is true. Fourth line says B is false. We finished that column. We finished the second premise. Now we just look at the conclusion. We just start over. Once again, this tells us on the first line A is true. So write true underneath that. Second line says A is true. So write it underneath there. Third line tells us A is false. Fourth line tells us A is false. So now we've finished. We filled out the entire truth table. How do we use this to assess an argument for validity? Well, we know that a valid argument could have every arrangement of truth values except one. A valid argument can never have this: true premises and a false conclusion. So let's go line by line and see if we were ever able to get true premises and a false conclusion. Now, when you fill this out, sometimes you might have all the truth values in here. Depends on what you're comfortable with. You might write them all out like this. And then at this point, it's hard to see what the relevant truth values are. And so you're going to want to do something to single them out. Circle, perhaps, the truth values underneath the main operator there. And then these and those. So you know which ones you're supposed to be looking at. You're not supposed to be looking at these, because if you do, you're going to get the wrong answer. You're looking at the ones that we've designated. So let's start with the first line. What happens when A is true and B is true? We get true, true, true. So didn't get true premises and a false conclusion. What about the second line? What happens when A is true and B is false? Well, we get false, false, and then a true conclusion. That's not what we're looking for. Let's look at the third line. What happens when A is false but B is true? We get true, true, and a false conclusion. True premises and a false conclusion. A valid argument is one where it's impossible, inconceivable, where it can never be the case that the premises are true and the conclusion is false. But here, it is possible. When is it possible? It's possible when A is false and B is true. So this argument must be invalid because it admits the one thing valid arguments could never have. Invalid arguments can have every arrangement of truth values, but there's one they can have that valid arguments can never have, which is, once again, true premises and a false conclusion. So remember, when we talk about an argument being valid, we're not saying anything about its actual truth values. We're not saying the premises are true or the conclusion is true. We're not saying the premises are false or the conclusion is false. When we talk about validity, what we're talking about is possibility and impossibility. When we say an argument is valid, we're saying one thing about it is impossible, that it could ever have true premises and a false conclusion. And since this argument clearly can have true premises and a false conclusion, the argument is invalid. Let's do one more argument, evaluate one more argument for validity using a truth table. And here we just have one premise and a conclusion. So instead of looking for two true premises and a false conclusion, at the end, we're just going to look for a true premise and a false conclusion. The process is always the same. Pull out the statement letters to the left. So we have H, we have K. What happens after we pull out the statement letters to the left? We figure out how many rows there are going to be. When there are two letters, 2 to the n, or 2 to the second, the number of letters, we get 4 rows. So we're going to have 1, 2, 3, 4. We start on the left-hand side, divide and conquer. Do top half T's, bottom half F's. So T, T, F, F. And the last column is always just alternating. T, F, T, F. Now that we've got the truth table set up, we just go line by line and treat this as basically 8 separate problems. So forget about all this over here right now, and even forget about this. What matters is this first line. It says H is true and K is true. Well, what happens if we have this claim and we're told H is true and K is true? When we have parentheses, we need to make sure we work from inside the parentheses to the outside. And it's tempting at first to think that this tilde is negating that H, but it's not. The tilde is really negating the result of what's going on the inside here. So we leave that tilde alone at first. You almost have to just ignore it. Forget it's out there and just focus on what's going on the inside. And a conjunction which has both parts true is a true conjunction. The only time a conjunction is true. Okay, we've got that done. Now we can look out further and see what else there is, and there's that negation. So we got true underneath the and, but the tilde says whatever you get for that and, I'm going to change it. So since we got true, out here we get false. We're sure to write the false underneath the tilde because that's where it belongs. That's what's false. The tilde. It's not the and. So we don't want to write this out in such a way that we kind of do some things in our head real quick and figure out that the answer is false, and so write false under here. Because the and claim isn't false. What's false is a denial of that and claim. So we got false for that, and hopefully it's easier for you to do a simple problem like this and to work from the inside to the outside. Well, that's what we're just doing over here. We're told H is true, K is true, and we got true for the and, but then we went to the outside and made it false. We got one line done. Now, line 2. In this case, they tell us to imagine H is true and K is false. All right, let's treat that as a separate problem. Imagine H is true and K is false. Forget about this part for the moment. For a conjunction, it's true in only one case. The only time a conjunction is true is when the left side is true and the right side is true. Well, that's obviously not the case here. So this conjunction is going to be false. Or another way to think of it is that for a conjunction, anytime any one component is false, the whole thing is false. It's easy to make a conjunction false. It's easy to ruin a conjunction. All you need is one false component. Now, we kind of step back and see, okay, we have that tilde there. So this tilde is negating our answer on the inside here. So that means we're going to get true underneath the tilde. So the answer is true. So true, false, gave us false on the inside, and we got true on the outside. 2 lines done. Now line 3. This one asks us to imagine that H is false and K is true. Okay, well, let's forget about everything else for the moment. Forget about all this. Forget about everything we've done thus far. And just focus on this line in which H is false and K is true. Anytime a conjunction has one false component, the whole conjunction is false. But that's not the end of the problem, because this tilde negates what we get on the inside there. And so the answer is true. So once again, make sure that you're not thinking of this tilde as somehow going with the H. If it were going with the H, it would be written like this, not H and K. That tilde is negating the H. But up here, this tilde is only negating the result, not the H itself. So let's see, we got true for that. Why? Well, because we're told H is false, K is true. A conjunction that has one false component is automatically false, but then the tilde turns it around and we get true. And the same for the last one. We can treat it as a separate problem. And consequently, we can just sort of ignore all this stuff and just single out the fact that H is false and K is false. So what happens there? Well, when a conjunction has at least one false component, the whole conjunction is false. So 2 false components is definitely going to make it false. But once again, that tilde is waiting on the outside patiently for us to get done with the inside. We work from the inside to the outside. So we've got the inside now. We go to the outside and we turn it around to true. So we get false, false on the inside here. That's a false conjunction, which makes that true. Okay, we've got that done. We did, in a sense, 4 separate problems on one truth table by just taking each line by itself and figuring out what the resulting truth value would be for this whole claim. So now let's go over to the conclusion. and start with line 1. The conclusion says not H and not K. Here we're told H is true and K is true. So what's that going to make not H? It's going to make not H false. That's going to make not K false. And if you have a conjunction with at least one false component, the whole conjunction is false. So we've got the first line done. Now, line 2. This tells us H is true and K is false. So let's go over to that conclusion. H is true, so not H would be false. I'm going to write the false underneath the tilde. K is false, so not K would be true. So what we really have is false and true, which makes that conjunction false. Now if you want, you can write everything out here. You could say, okay, on this third line, H is false, K is true, and then since H is false, not H would be true, and not K would be false. True and false gives us false. But once you get comfortable with it, it's helpful to be able to do some things in your head, because you can see this is a lot more messy than what we have up above. It's easier if we can just think real quickly that, well, H is false, so that's going to make not H true, and K is true, so that's going to make not K false, and just write the false there. And finally, our last row, H is false and K is false. Well, if H is false, not H is true. If K is false, not K is true. The only time a conjunction is true is when both parts are true. So we're done with this part at least. We've got the truth table filled out. What are we looking for? Well, a valid argument could never have true premises and a false conclusion. So we need to, when we're comparing the premises and the conclusion, and we've got all these truth values up here, single out the relevant columns. So I'm going to circle this one because that's the one we need to be looking at, and circle that one. This helps because sometimes what students will do is they'll compare this F with this F here, or this column, and they end up getting the wrong answer. We need to make sure that now that we've filled out the whole thing correctly, we're comparing the right columns. So let's go with the first one. We get F for the premise and F for the conclusion. That's not what we're looking for. Second row, we get true for the premise, but false for the conclusion. That shows the argument's invalid. We don't even need to go further, but let's just look at the third line. We get true for the premise, false for the conclusion. Again, shows that it's invalid. And last line, we just get true for the premise and true for the conclusion. All we needed was one line with a true premise and a false conclusion, and that would tell us this argument is invalid. Since we got that, we judged the argument to be invalid.